Good evening. We'll start in a couple of minutes. Okay, we'll start now.
Yeah.
So, good evening, everyone. My name is Umer sir. I am a PhD scholar at the Department of Mechanical Engineering at IIT Madras. And welcome to the doubt session 10 for the course Finite Element Method, Variational Methods to Computer Programming. So, uh, till week 9, I think we had we started with the 2D FEM, and so I'll just quickly summarize. We started with the basics of variation principles, and then we extended the discussion to 1D finite the steps in finite element method. We discussed the basic procedure in an FEM in any FEM problem. Then we started with the 1D FEM. So in 1D FEM, we discussed some example problems specific to structural problems. So we did 1D bar problem, beam problem, truss problem, beam problem, and then a generalized verti frame element problem. Then we did some basics of the this, vector calculus to start with the 2D FEM. Then then we discussed 2D FEM and started with scalar variable 2D FEM problems. And then last week we had done some vector problems in 2D FEM. So we discussed a classical example of elasticity problem. So I think by the starting of this week, we concluded the discussion, and we did study some post processing. So if we get the solution as alpha, which contains the displacement in x and y direction uh, for all the nodes. So we if we multiply it with the matrix P, which is nothing but which is symmetric operator operated on the displacement. This product will give us the strain, and again multiplying the strain by the elastic constant tensor D will give us the stress. That is something that we had discussed before as well. So next is the computer program implementation. So we this course we studied a nice algorithm to program the steps in the 2D FEM problem. So as we had seen the algorithm in 2D scalar value FEM. So this the same way the program is designed for the vector valued problem, except only the integrand part is changed, and now instead of the n matrix or the gradient n matrix, we need to find the b matrix. So which can be calculated using the gradient n matrix. So the procedure is as follows. So we find the gradient of uh, ni in terms of the natural coordinates. So this will give us in zeta eta coordinate system, and if we multiply it by the inverse of the transpose of the inverse of Jacobian matrix, we'll get our gradient ni matrix, which will give us gradient ni matrix, which would be in the xy coordinate system. It will give us ni comma x. So this is n1 comma x, n2 comma x, comma x, n4 comma x. Likewise, n1 comma y, n2 comma y, n3 comma y, n4 comma y. So with the help of this matrix, so we denoted this as bn1 comma 1, like that. So with the help of these elements, we can design the b matrix. So so then we discussed the basic program, and that concluded the discussion on the 2D scale vector valued problems. That is the elasticity problem in FEM.
Ume, you have written this B matrix as dn 1 comma 1, dn 1 comma 2.
Yes.
This dn basically the derivative of this shape function with respect to the space coordinates, or what it is dn.
Dn is basically a representation of the gradient of this ni. So ni is basically you say that ni is just n1, n2, n3, n4.
Okay.
And if we take
Okay.
gradient of this, we'll get
Mhm.
n1 comma x and n1 comma y, n2 comma x, n2 comma y. So all
Yes.
these, I'm not sure about the specific order here, but it is a collection of all this data.
Yeah. Yeah. Yeah.
So and here we've shown how to convert it from the natural coordinate system to the XY coordinate system.
Okay.
then we use it to design B.
Okay.
Okay, so yeah. Okay, so this concludes the discussion on 2D FEM, the vector world problem in 2D FEM, but not completely. There were a couple of things we discussed more. That is the super convergent points. So super convergent points are basically the points where derivatives of the solution converge fastest. So this is not something which is specifically related to scalar value 2D problems. It is a generalized concept in FEM, in any even 2D FEM. So there's a fact that we heard we which we hear quite a lot. That is the uh, the the solution converges fastest on the node of the elements, or we kind of get exact solution at node in certain various problems. While there's another fact that the derivative of the solution would converge fastest on the Gauss points.
Okay.
So yeah, so in some cases, in some basic problems, we get the exact value of solution, the derivative of the solution at the Gauss points. So
Okay.
so in FEM, if we have to take derivatives, we see that the derivative is not continuous, because we don't when we are taking the assumption of the solution, we don't ensure the continuity of derivative in the FEM domain. So to deal with that discontinuous behavior, we find the super convergent points for the derivatives, and we join those points to make a continuous function, sort of. So that's the use of super convergent points.
Now, Umar, can you describe this phenomena of convergence? For example, we are talking about the convergence of the NEFEM problem.
Yes.
So basically, convergence means is it related to that there should be any such kind of level of error in FEM results which should be gone through a certain threshold limit, or something else, or what is the actual meaning of this convergence in FEM?
So what you're saying is right. So in FEM, if we in very rare cases, if we know the solution, we'll
Mm-hmm.
see that the as we do some kind of error, any action that reduces the error. So we say we are refining the mesh.
Okay.
So you'll see that the solution would approach that exact solutions.
Okay.
So
Okay.
we see that it is converging.
Okay.
Converging means its value is stabilizing. And
Okay.
if in most of the cases we don't know if this what's the exact solution, so we set certain criteria that
Mm-hmm.
if we keep on refining, our solution value says increase is changing, and the
Mm-hmm.
change keeps on decreasing. So if
Mm-hmm.
we set certain criteria that that change that is below that tolerance value, then
Mm-hmm.
we say it is converged.
Okay. Okay.
So that is actually the definition of convergence.
Okay, and the criteria can be in various forms, because as I have worked in ANSYS Workbench, and now I am also working on Abacus CAE. So
Yes.
basically, there are two, three criterias in there. What I am observing nowadays. First is the residual displacement. Second is the residual force, or
Yes.
etc. etc. So actually, this residual value, as per your suggestion, it indicates the level of error in our FEM solution.
Yes, right. Exactly.
Oh, okay, okay.
Yeah. In some cases, I think energy is also used as a parameter.
Yeah, that is used in explicit solutions.
Okay, okay.
Yeah, and LS Dyna is one of the explicit solver in which we use the error in energy. So basically, I think what is there? There is a first law of thermodynamic principle. I think that is, so. Energy balancing is done by software when we define any input file to the software. So
Okay.
on the basis of that, it will calculate the error in energy. Yeah.
So next is the it's not directly taught in the lecture, but I kind of thought it's good to keep it. This is the heading. That is the error in FEM.
Okay.
So we I think we haven't specifically talked about, but I have some problems we can discuss. That is also will be useful.
Hmm.
So error is basically the difference in the exact solution and the finite element solution.
Hmm.
So there are a certain number of ways to evaluate this error. So there's
Hmm.
nothing fixed, but there are certain ways like that there can be point error. We can define error at a point,
Hmm.
and there are other like error L2 norm, error energy norm, and like this.
Okay.
So here I think in this class we discussed only energy norm. So
Okay.
basically we find the difference in the energy and integrate it over the domain.
Okay.
So that's why that way if we are defining in terms of energy, we have it in terms of stress and strain.
Okay.
And it is interesting to keep it in terms of stress that way. So it's error is basically difference of the exact solution and FEM solution, and most of the cases we don't know the exact solution. So if
Hmm.
we keep it in terms of stress, we can keep the exact solution as the recovered stress. Recovered stress means the stress achieved from the joining the super convergent points. That would
Okay.
definitely be the stress with least error.
Okay. Hmm.
So
Okay.
there's one interesting point. I think it's not discussed in this lecture, but I remember it from a past course I took that the energy calculated by FEM is always higher than the exact solution.
Okay.
So FEM kind of overestimates the energy of this. I forgot its proof, but it's something I can remember.
No, I think it is something related to the fact that, for example, if we convert one 50-meter cube bubble into the 50 equal 1-meter cube bubbles, then definitely the surface energy stored by those 50 individual bubbles, if we sum those up, and if we calculate the individual 50-meter cube bubble, then definitely then surface energy level of those individual sum will be always higher than the this higher size, I think so.
Yeah,
Because
I think what you mean is that is some non-linearity.
no, 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 it doesn't mean non-linearity actually. For example, if we talk about a individual cantilever beam and we are calculating the total strain energy stored by the cantilever beam, now what I am doing, I am converting those cantilever beam into some 40 50 elements.
Yeah, I got it. Yeah.
Yeah.
I can't remember the exact concept, but I read that something like this in SOM from
Yeah.
FEM
Yeah.
model.
Yeah.
Okay, yeah. So yeah, this is a fact we can remember.
Mm,
Next interesting topic we discussed was of adaptive refinement.
yeah.
So adaptive refinement means we define certain part of the domain more than the other part of the domain
Okay.
based on the error. So this can be done in two ways. One is by selectively refining only certain part on each step. So we evaluate the usually we do that we evaluate the error in the whole domain, and we identify that if the error is exceeding certain value, we
Okay.
identify mark those cells, and we only refine those cells selectively.
Mm-hmm. Okay.
So I think you might have seen this in some of the solvers
Yeah, yeah,
lectures.
yeah, 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 yeah. I have seen. Yeah, even if our for example we are facing some convergence issue, and especially convergence issues are arrived only means what I have observed in my career when you are assigning some non-linear things in your solution. For example, there is some frictional contact or no separation contact in your solution. Then
Yes.
what solver will do, it will automatically adjust the stiffness value again and again and again and again. But if we refine the mesh at those particular contact areas, then the chances of the solution to be converged is high.
Yes.
Yeah.
So it's I think used in problems like crack propagation also.
Yeah.
Uh,
Yeah.
there we need more more accuracy near the cracked surface.
Yeah.
So as it proceeds, I will see that the mesh is getting refined there.
Yeah.
And
Yeah.
I work on phase field modeling. It's also useful there. I did try it once in my model.
Hmm.
So in
Okay.
phase field modeling, we have an interface moving. So there's the one
Okay.
phase in certain part, another different phase in another part,
Okay.
and between the interface, there is
Hmm.
something called phase field parameter, which very smoothly. If
Okay.
you consider this domain here, so say this outside we have p equals 0 is one phase, p
Okay.
equals to 1 is another phase. So this
Okay.
interface has very small width. So
Okay.
we need more accuracy in this area actually. So it keeps on
Okay.
moving. So as it moves, we see that if we apply adaptive refinement, we see that the
Hmm.
mesh getting refined on along this interface, and
Okay.
as it moves inward, that mesh again gets coarsened.
So you did this thing in any preprocessor or solver, or what was it?
I use a library till 2, so
Okay.
I did add that part into my code. So it's kind of the structure is like any MATLAB code.
Okay.
So I added a part of adaptive refinement. I used to check some there is that library provides many interesting functions. One was Kelly error estimator,
Okay.
so that automatically calculates the uh, some form of error in all the cells, and if
Hmm.
we mark that, so for me the error was basically if the value of phi is between 0 to 1,
Hmm.
that would it signify that I have a interface in that region.
Okay. Okay. Okay.
So that will mark those cells, and it will refine those cells.
Okay. And you were interested to see the deformation pattern of this film, or what was the expected result here?
So for me, the interesting thing is how this interface moves inside.
Okay.
So in usual cases, it moves quite smoothly. But in fact, the problem I ran for this, it was not like this. It was
Okay.
like it was the peritectic problem. If you heard of it, in
Okay.
peritectic problem we have three phases.
Yes. Yes. I think two solids,
Yeah.
and yeah. Yeah. Yeah.
So this is some gamma solid, this is delta solid, this is liquid. So
Yeah.
this has to grow on this between these two.
Okay.
So for me it was this movement.
Okay.
I don't know if I have some recording of that I can show you.
Okay. Means this FEM we can also use to define to study about the microstructure.
Yes. That's what kind of I do.
Yeah, actually, I didn't see this type of thing in industry. Even very bigger MNCs I have visited in my life.
Okay.
Yeah.
See if I have any results. can't find that adaptive refinement part. Right, some clip of it.
Okay. Yeah, but what you are finding, you can show because these type of things I didn't see anywhere.
I have some other clip, but let me see if I can get for adaptive refinement.
Okay.
Where I can show you this. I have so in
Multi-phase field bonding. Okay.
there are a couple of problems I did. The upper one is two-phase solidification. So
Okay.
I did dendrite formation, while only single phase liquid converts to single phase solid.
Okay.
And then lower one is the peritectic actually.
Okay.
I have
Okay.
shown mesh here. I am looking for that where I have shown mesh.
Okay. You want to show the adaptive refinement technique that you have used in this.
Yes, yes.
Okay.
Yes, it's not here. I think must be in my other system. Okay, so we can see if you want we can okay we wanted to discuss more here, right? Let's discuss that.
Yeah.
Let me go back to my other screen. Okay, so this was one way to do adaptive refinement. Another is
Okay.
that we can just straight away uh, know where the define wherever we want fine mesh, and we can
Hmm.
regenerate them. So okay, that sorry missed something. That this kind of refinement. So suppose we have two chord elements here, one
Hmm.
5 6 and 2 3 4 5.
Hmm.
Suppose if you want to refine 1 to 5 6 cube square.
Okay.
So
Okay.
we have refined it using these red lines. Now one issue comes up that this extra node created here, this one.
Yes.
This is fine with the other four chord elements, but this creates issue with this 2 3 4 5 element. So now it has one more degree of freedom.
Yeah.
So it's called hanging node.
Okay. Okay.
So usually, what solvers do is they don't consider this as a new degree of freedom. They just assign this solution value by interpolating the solution value at the neighboring nodes.
Okay.
So that's how most solver deal with it.
Okay.
Another way of refining is we just regenerate the mesh based on wherever we want uh, finer mesh. So
Okay.
if you want, we can do a little demonstration on Gmesh for that.
Yeah. Yeah. Yeah.
I'll open Gmesh here. Okay, so I hope my screen is visible.
Yeah. So this software is made by IIT Madras itself, or
Gmesh, I think, is I don't remember who made this, but it is made by some other group. It's quite famous, quite old, I think.
okay? So this is the we can say the more common tool used in industry also, I think.
I think so.
Yeah.
So in our research group, we usually prefer working on open source tools.
Okay.
So this is one. Okay, as we add the lines. Okay, so this is geometry with some sharp edge.
Okay.
So this should give us directly something. So Gmesh actually takes care of this thing directly.
Mm-hmm.
Okay, 10 mesh there.
So this is the 2D platform you are selecting to draw something.
Yes, yes. So I right now I'm drawing only 2D mesh, but we can do
Mm-hmm.
3D as well.
Okay, so you are using the sketching tool.
Yes. So we can add basic 2D geometries. We start with I started with point, then join them with line. There are others
Okay.
also. You can do the
Okay.
circle, the ellipse, and all that.
Okay.
Okay. I forgot defining a plane surface. So after making a 2D mesh, we have to define a 2D plane.
Okay.
Okay. So right now we have quite a coarse mesh here. You can
Yeah.
see the green lines.
Okay, so you are using Traya.
Yes, yes. We can change that too.
Okay.
Can have chord mesh also.
Okay.
I can change element size factor to change the size of the elements.
Yeah, that
Suppose
is.
now if I want a really fine mesh at say this point.
Mm-hmm.
So you remember when we were adding points here,
Mm-hmm.
we have four arguments here. So first three are the XYZ coordinate values.
Mm-hmm.
Fourth one is the size of mesh we want around here.
Yeah.
So I defined it as one. By default, it's just one.
Yeah.
So I define it as one, and if even my mesh. So in the all geometry options here, so I had my element size vector also as one.
Okay.
Before I changed it, was one. So there, my mesh here would have roughly the size around one. When I had triangular meshes, it was actually exactly equal to one.
Okay.
So if I change that parameter, so I can edit the script. I don't know if you can see it here. Yeah, I can edit the script whatever I did here.
Okay.
One, I have to save this first.
Yeah, save mesh option is there below.
That is to save mesh. I don't want to save mesh. I have to save it as a geo file to make it editable.
Okay. Okay. Yeah, I think there was. Can you just go back to that file?
The save model options. There was should be some
Y-
other save
Yeah,
options.
you can export this. You can export this also. Go to the file, because in export there are many options there. You can choose
Because
whatever.
actually, in export we get the extension option to as a mesh file.
Yeah.
But right now I want okay, I have geo option here, right?
Yeah.
But that's geo unrolled. I want geo only.
You
So
you can directly click on the this arrow. Yeah, you can click here. Guest from extension, click here.
okay, I'll see. Okay, it is that output is not supported for saving mesh file actually.
Okay.
Anyway, I'll see.
If you want to see these things in detail, I am suggesting you one very popular preprocessor, that is ANSA preprocessor. This
Okay,
this preprocessor is made by the company Beta CA System, and you can define anything you want to apply as a boundary condition, any type of load, any you can use even cohesive elements also in that.
okay,
Okay. Yeah. ANSA preprocessor in nowadays is the best software to be used in industries.
okay.
Yeah.
So we'll just see here.
Yeah.
This is a mesh that I had produced earlier.
Okay. Circles.
Okay, so I have multiple points here to control mesh size here.
Yeah.
So I'll just open the script and edit the mesh size option anywhere.
Mm-hmm.
Let's see. Let me show you. Not yet. Make a new.
Okay. So I think you are not the perfect guy for file handling now.
Yeah. It is getting really complicated. My screen is filling with windows.
Okay. Okay. Okay.
I am actually used to using this on Linux.
Okay.
So,
So you are good to use the Linux.
yeah, yeah, yeah.
Okay.
So all these things are really quite easy in there.
Hmm.
And
Yes.
open
Yes.
source software is rather much easier than Linux.
Hmm. Yeah.
So
Torrents.
I'll define first this one as okay, then or this point also as this. This point I'll define this message as point one.
Okay.
Then again this point here. And go ahead 0 0 1 0 1 1
Okay.
0 1 should be here, right?
Yeah.
Made a mistake in adding the coordinates.
Yeah.
Okay, we are here. So now we add line. Then we define a plane surface. Now we mesh it.
Hmm.
So you see, this point here, we defined a smaller mesh size here.
Hmm.
Rest of the 3 point, we defined a larger mesh size. So you see the
Yes.
mesh reduces here.
Okay.
If I increase it, reduce it even further,
Hmm.
I'm changing it in the geo file here,
Okay.
and I'll reload the script. Then mesh it again. Where is it? Okay, okay, okay. So again, I didn't add the plane surface here.
I think you have to load the sketch first.
Okay, okay, okay. Oh, I edited the wrong file and I left with no lines here, only points. Surface. Okay, shit.
Yeah. Now it will work.
Hopefully.
Mm, it should.
Yeah, yeah, yeah. Now we see the mesh.
Yeah.
So now it's even smaller. You can
Mm-hmm.
see the difference in the mesh size.
Yes.
Okay, so that was quite painful, but we did it. All right, so I'll stop sharing the screen. Okay, so we have done the 2D FEM scalar value problem and some extra topics. So
Yeah.
let's quickly finish this. So then we started with the eigenvalue problems. So
Mm-hmm.
eigen basically means the characteristic of any system,
Yeah.
and for we study it for dynamic systems, and certain example is the vibration in bars and beam problems.
Yes.
So we take an example of the vibration in bar 1D bar problem.
Yeah.
So now we have, since it's a dynamic problem, we'll have an
Mm-hmm.
acceleration term also in our
Yes.
bar equation. And since it's a time dependent problem, okay, so we have the boundary condition as the normal usual reset boundary condition as the and the normal boundary condition.
Mm-hmm.
In free vibration problem, we keep the load as zero. So our normal boundary load P will also be zero, and the uh, distributed load will also be zero.
Mm-hmm.
So at the end, we'll have be left with only this equation.
Yes.
So to solve this equation, we have our u as, now as a function of displacement and time. So we'll
Yes.
break it down, and at the end, we'll be left with these equations. So
Yeah.
particularly this equation
Mm-hmm.
for auxiliary motion. Now we find the weak form for this equation, and we'll discretize it in terms of the shape function, and at the end, we'll be left with the eigenvalue problem.
Yes.
So in linear algebra, eigenvalue problem is there's something called an vector for any linear transformation.
Yes.
So suppose T is our linear transformation, which is nothing but a matrix. So if this linear transformation acts on any vector V,
Yeah.
so every linear transformation, there exists some vector when on which if this transformation is applied, we get some constant time that vector. So this vector is actually called the eigenvector, and this lambda constant is called the eigenvalue.
Okay.
So this actually define in this is talking in terms of linear algebra, but in physical system, lambda determines the characteristic of the system.
Okay.
So yeah, this here becomes the eigenvalue problems, and if we want to find the eigenvalue, we just need to calculate the determinant of k minus omega square m. This will give us equals 0. So solving this will give us our omega square, or we can say lambda.
Mm-hmm.
So this way we can find the eigenvalue uh, for the given system.
Okay.
So this is the end for this week's content, and if there's any doubt, we can discuss this. Discuss anything related to what we've discussed so far.
Umair, first of all, I want to ask you ever did a model analysis on any solver in your academics and as you are doing some research work?
A solver in the sense, what kind of solver?
Means, for example, I am writing some input file for the element distribution file. That is called the INP, which contains the boundary conditions, means complete model details it is containing, and I am running that on one of the solvers. And
Okay.
so my question is, when we do model analysis and free model analysis, if I'm talking about, and because in free model analysis there is no any external load applied, and even body forces also we are not considering. So basically, when solver will decide the mode shape of our FEM structure, so what type of load it will consider, means I didn't get the actual thing, how it is defining the mode shapes, how it is defining the displacement values for the particular mode shape. For example, there is any shear mode or any torsional mode or any bending mode, how it is deciding,
Okay.
because load is completely absent there. So to
Uh-huh.
to limit the displacement value, we have to define some load, because stiffness matrix we have, and to define this alpha we need something in our hand. So how it is deciding the same thing?
Okay, okay. You mean to say to get any what do we call it? Uh, mode of vibration,
Yeah, any mode
how
of
will
vibration. Yeah.
what kind of what drives it? Is it
Yeah, what drives it? Yeah.
since all loads are zero? I
Yes.
think I am not much familiar with these dynamic systems, but I think it can consider some initial excitation, and after that initial excitation, it is free on its own, that movement.
Okay.
So there's an assumption of initial excitation, and that is all the input there is.
Okay, so what we are assuming while we derive the elementary equation of vibration in our system, that for example we are giving some an arbitrary excitation to our vibration system, this type of
Yes,
thing, I think.
yes.
Okay, so each and every solver, I think the programmer has fixed these excitation function or what it is.
I'm not sure how that works
Yeah,
because I haven't
yeah,
worked with any solvers,
yeah, yeah,
but I
yeah.
think so, maybe.
Okay. Actually, this question I was asked by an employee in a company. So, but
Okay.
at that time I was unable to give the correct answer. So,
Okay.
yeah.
Yeah, I think it works on the some initial excitation. Apart from that,
Okay.
there's no intermediate forces. There are cases of when forces are there, but that that is I think a different problem then.
Yes,
We've
that is
seen
called that is called pre-stress model analysis. That is called.
okay. I remember something related to what we studied in vibrations in our undergrad.
Okay,
There
okay,
was something.
okay.
Okay, so anyway, this is how we get the eigenvalue. We conclude this.
Okay.
Are there any other doubts?
No.
Yeah. Okay, so then we can move on to problem discussion.
Okay.
Okay, so evaluate the BE matrix for an element with coordinates given as these.
Yes.
So this is the quadratic element. First of all, what all do we need? Node 1, node 2, node 3, node 4. So either we can just have the shape function for this element, or we can go about. transform this into our natural coordinate system or the master element
Yeah.
where we have these coordinates. So for this master element, we know directly now
Yeah.
psi1 equals
1 by 4 1 minus psi 1 minus eta.
yeah. I think these are the shape functions. So we can define a mapping as psi I xi,
Yeah.
so which will give us that is 0 here. So we'll have psi 3 plus psi 4
Mm-hmm.
because yeah x is 1. No, 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 no. I think psi 2 and psi 3, isn't it?
Yeah. Psi ixi. Okay. Psi 3. Yes. Yes, it is. Yeah.
We'll have what is common between psi 2 and psi 3 is 1 plus psi.
Yeah. And then next bracket is 2.
Then here we have 1 minus eta, 1 plus eta, that will make it 2. That's 1 plus xi by 2. For y we have, so we have only psi 3 and psi 4 here. So what's common is 1 plus eta, 1 by 4, 1 plus eta. Then we have 1 plus xi, 1 minus xi,
Yeah.
2 again. So eta by 2. So firstly we need the Jacobian matrix.
Hmm.
So that is, I think, dou x by dou xi, dou x by dou eta. Correct me if I am wrong anyway.
Yeah.
I
Yeah.
think,
Yeah. Yeah. I am watching the calculation.
yeah, thanks. So dou x by dou xi is half,
Yes.
then 0, then 0, then half.
Yeah. So always it comes 1 by 4.
Yeah, yeah. So to find BE matrix, what do we need first is uh, first of all the this gradient NI matrix in terms of uh, eta zeta. So we want n1x, 2x, sorry, sorry, xi, eta, n2 eta, n3 eta, n4 eta. So this would be 1 by 4, we can take common everywhere.
Yes.
1 by 4 times minus 1 minus eta, 1 minus eta, okay, 1 plus eta, minus 1 plus eta. Then we have minus 1 minus xi minus 1 plus xi 1 plus xi 1 minus xi.
Hmm. Yes.
And next is we need the inverse of this Jacobian. So that
Yes.
should be inverse is 1 by the determinant
Yes.
of the transpose, right?
Yes.
So transpose would be same thing.
Yes.
And then we'll take the transpose of this again. That is also same.
Yes.
4 times this. So at the end, uh, gradient ni would be okay. I think this should be the transpose of this, right? So transpose of this.
No, this is a step I didn't understand.
Which one?
You wrote this J inverse equal to 1 upon 1 by 4. Okay. Okay, okay. So you made inverse of this J first.
Yes,
And
and
then
then the
again,
transpose.
okay. And then you, okay, okay. Yeah.
So the formula was something like this times. So this should be that is just 2002 times. Yeah, I think that this was right.
Yeah.
And there's no transpose here. So if we multiply it, we get 1 by 4 is already there. So we have the first row will have 2 times the first row, right?
Yeah.
So we can just simply write the first row as 2 times the first row, and the the bottom row would also be 2 times the bottom row, right?
Yes.
So we can just take 2 outside.
Yeah.
So at the end we'll have half of, yeah, because we can just take away two from this, right? And it's just
Hmm.
receding.
Yes.
So we
Yeah.
have half of, or we can just say it as 2 times. Okay, so now if you want to define the B matrix, so we start it with the first element of the gradient Ni. So that is, we still have half here. We keep the half here. That is 2 times 1 by 4.
Yes.
So that would be 0. 1 minus eta 0. 1 plus eta 0. Minus 1 plus eta 0. Then we
Yeah.
have 0 minus 1 minus xi 0. Minus 1 plus xi 0. 1 plus xi 0. Minus xi. Then we have minus 1 minus xi 1 minus eta minus 1 plus xi 1 minus eta 1 plus I 1 plus eta minus I minus 1 plus eta. So this way we can have our E B matrix.
Okay.
So this is just the demonstration to get the B matrix, and in our solver we'll be evaluating B for a certain Gauss point, right?
Okay.
So there we can just substitute the value of E times I for that Gauss point because
Hmm.
it is under the integral sign, right?
Yes.
So there we'll just add substitute the E times zeta with the E times I with the particular
Coordinates. Yes.
coordinate of the Gauss point.
Yes.
Okay, so this is how we get B. Now, if we have we are given the displacement vector, that is the alpha. So how do we get the strain tensor?
Okay.
So this is strain is
Space gradient, I think. Space using the space gradient.
yeah the u. So this actually becomes, so we just multiply this vector with this matrix.
Yes.
So instead of doing this painful task, we can do it in MATLAB, I guess.
So these are there are four values in this transpose matrix, or what it is written? Point zero zero. Okay, eight
Eight
values.
values,
Eight
yeah.
values. Okay. Okay.
Let me share my MATLAB window.
Okay.
So so we can define a function first.
Well, in this step, I had a doubt. Uh, when we
Yes.
define any function in MATLAB, for
Yes.
example, we are defining some integrand as a function.
Okay.
So how is it stored in library already, or how it determines that it will calculate the integrand based upon the input we will give?
Mm, So you mean what kind? So I'll just open a function I have.
Hmm.
So this is the function that
Okay.
gives the output of the shape function dn.
Yes.
So the gradient of the shape function.
Yeah.
So suppose this is some integrand in part of some integrand in any integrand for a K matrix.
No, for example, this case you are defining some uh, derivative of this shape function here. So how it will calculate, because it doesn't know what user is trying to do.
Yeah, it only gives output for dn. So suppose I define a function It
Mm-hmm.
gives me some integrand as output, and it
Mm-hmm.
takes input as the xi and eta values, right?
Okay. Mm-hmm.
How do we end a function?
It
Okay,
is.
it's end.
Yeah.
So now I'll give the say eta into xi, this this right.
Yeah.
I'm missing something here. Okay. I have to give name of uh, cos integral. Okay, isn't it enough?
Mm,
Okay, invalid file name. Okay, I just changed. Okay, so I have this integral here.
yeah.
Okay, okay, okay. Change it as function file. Okay, I don't want it to do that. It
Yeah.
should create another script. But we can create a function in a script file also, right? We just do
Yeah.
that anyway. So now I call a loop for I equals. Uh, so I define the Gauss points here first. Gauss points are skip 0, 0,
Mm-hmm.
Gauss, and the weight is 1.
Okay.
So what should be our value of integration?
Eta into xi. It will be zero.
Okay, it will be 0 here, right? But what is the way of calculating the integration using Gauss quadrature? We
Okay.
call the integrand.
Mm-hmm.
The integrand here is this, and we give input as the Gauss point, right?
Yeah.
Right, and we multiply it with the weight function. So this will give us the integral.
Mm.
Suppose we
Okay.
had more Gauss points, we could have done that for though we could have run a loop. So what I'm saying is that our function whatever we have defined so far, it gives us the value of the integrate the Gauss points.
Okay.
And in our main function where we are calling that integrand, we are doing some kind of loop that sums up the value of that integrand at the Gauss point while multiplying with the corresponding weight function.
Okay.
That is weights.
Mm-hmm.
So
Okay.
that's how we had been doing. Anyways, I was doing something else. How do I put some missing here? Okay, that's how you define an array in MATLAB. I am not used to MATLAB. I
Okay.
apologize for that.
Okay.
Don't know. So anyway, yeah. So that's how we do it. So I was going to do something else here. So we can define. Okay, we can just directly define B matrix.
Okay.
0 minus 1 minus 0, then minus 1 plus eta, then 0.
Yeah.
Then we have 0, 1 minus 1 minus side, then we have 0, then minus 1 plus side, 1 plus side, then we have 0, we have 1 minus side. Then we have, let's copy this. After 0, we'll add each of these terms. So we have last row minus 1 minus xi, minus 1 minus eta, minus 1 plus xi, 1 minus eta, 1 plus xi, 1 plus eta, 1 minus xi, minus 1 plus eta.
Mm.
So yeah, this will be the output for B, and
Yes.
we can just define B at 0, 0, and define strain at 0, and we are given u displacement as 0.001, 0, 0, 0.001, 0, 0.001, and 0.010. So that's how we take transpose, right?
Yeah.
I think it will not work outside a function.
Mm.
If you're
Yes.
writing a script file. I forgot how it used to take transpose.
But after transpose, it will be.
Is this how we take transpose here? Okay, I remember now. This is how we take transpose.
Ah, yeah, yeah. Dash.
Yeah, we have it 8 cross 1. So what we do is to find strain, we do call B. No, B is actually calculus times U. So we value the strain here. So this is our strain. See, 3 cross 1 vector.
Yeah.
Okay, so setting up it is a difficult task, but once we are done, its finding strain was just a one enter key. Then we have next problem. We can just find stress also using that. So we just need to define our d vector for stress. We can just copy it from somewhere. So if we define E as 200 and mu as zero point 0.3, we can define this as, so we first consider plane stress, maybe plane
Yes.
stress E divided by 1
New. 1 minus new.
plus
Yeah.
nu into 1 plus nu, right?
Mhm.
Isn't it?
Yeah. Yeah.
Uh, yes. So we had 1 nu 0. We have nu 1 0 guys. Okay. Then we had 0 0. This one was 1.
1, I guess.
No, no, I think it was 1 or 1 upon 1 plus nu or something. I sure it was 1. Let me just check here.
I
It was not
think
nu.
the outside that you have entered. Let me try.
Let me just check, open, pick up the notes.
Yeah, yeah. I'm also trying to pictures.
Yeah, for plane straight, it's actually 1 minus nu square.
Yeah.
And I think the stress is for plane stress. And it's 1 minus nu by 2. Yeah, rest all is fine, I think.
Yeah.
So we get the stress here as d into strain. Okay, so d stress. Yeah, so this is a stress. And if we want to define it for plane strain, we have E1 plus nu, 1 minus nu. We have 1 minus nu along the diagonal.
Yeah.
Here also we have 1 minus 2 nu. So our stress now is, okay, so these are the value of stress now. So changed values.
Yes.
All right. So we have done these two problems here. So the
Mm-hmm.
Yeah, so we have done this problem also. I'm just saying where the it was. Minus 1 is not fine. For in stress, our stress was finite 10659 to 0.0769.
Mm-hmm.
For plane strain, stress was 10.455 minus 0.195 to 0.163. So these are the results. Okay, move on to the next problem. Okay, so if the exact solution ux equals sine x is approximated as uhx equals to 2x pi minus x by 5 in the domain 0 to pi, find the point error at x equals 0, x equal to pi by 4, and pi by 2. So error is actually u exact minus ufm.
Yes.
So simply finding point error is we can just substitute the value of x. This is also 0 basically. So this is actually 0. There's no error here.
Yes.
So pi by 4 we see. So sine pi by 4 is 1 by root 2, right?
Yes. Minus 2 into pi by 4.
So just quickly do some calculator. We have 1 minus, so 2 minus
5 pi by 4. 3 pi by 40.
3 pi square by. So we have an error of minus 0.03. Then at pi by 2, we have sine pi by 2 minus 2 pi by 2 pi minus pi by 2. Sine pi by 2 is 1. Then we have pi into pi by 2.
Pi square by 10. Yeah.
We have 1 minus pi square by 10 is equals to 0.013. So these are the point errors. So you see that in an FEM domain, the error would vary point to point.
Mm-hmm.
So that's where this point-wise error evaluation is not it doesn't give much idea. We need to sum it up over the domain.
Yes.
So we'll see that in the next problem. So now we find the L2 norm, error in L2 norm basically. So error in L2 is actually the domain is 0 to pi. We take the difference, square it,
Dx.
take
Yeah.
root. So this is the formula. We have sin x minus 2x 5 minus x by 5 squared dx root of this. So I'll just quickly do this in calculator. Sine of x minus 2 into x into 5 minus x by 5 squared 0 to pi. This gives square root of 2.9 10 to the power minus 3. Take square root of this. We have 0.0538.
E.
So
Yeah.
this gives us a uh, quantification of error across this say domain, or if we do it for particular cells in an FEM problem.
Okay.
So this gives us an estimation of the combined error in the entire cell. So
Got it.
this gives us judgment on what is the situation of error in what part of the FEM domain, and
Yes.
and this is useful for refinement. So which type of convergence is more suitable for complicated geometry domain? So have you heard about H convergence and P convergence?
Yeah, I heard about. Yeah.
So yeah, can you guess what should be the answer for this?
But for actually, I don't know the actual difference between these two.
Okay, it's fine.
So
So basically, there are two types of convergence or the refinement we do.
yeah.
One is H refinement, another is P refinement. So H basically denotes the element size.
Okay.
So if we say that we are doing H refinement, that means we are refining the mesh in simple terms.
Okay.
And P refinement, the P represents the degree of polynomial,
Okay.
which we use to approximate the solution. That is the degree of the shape functions.
Okay. Got it.
So that P refinement means increasing
Order
order
of
of
the
the
shape function.
yeah, yeah. So both of this would uh, improve our result, reduce the error. Both of these techniques, but we have to determine which one is better for our situation.
Complicated geometry domain. Increase the order of shape function. Extra.
So in when the geometry is complicated, particularly in
Hmm.
this 2D and 3D FEM problems, there the
Okay.
main issue is uh, the inability of our standard element shapes to cover that complicated geometry. So
Yes. Yes.
the refining the mesh is a good choice.
Okay.
So for this for better convergence for such type of domain,
Okay.
it's advisable to do edge refinement,
Okay. Okay. Got it.
particularly in that part. In some problems, I think that's more practical. We do a combination of H and P refinement. Somewhere we perform H refinement, and some places we do P refinement.
Okay.
Okay,
So
so
in my next analysis, I will compare these two refinement.
yeah, sure, that would be interesting.
Yeah, yeah. But I didn't get the option to get the higher order shape functions in any preprocessor till now. I have to search for the same
Okay.
first. Yeah, means mesh refinement is in our hand,
Yes,
but
yes.
to select the order of the shape function, I didn't see in any preprocessor till now. So I think today, the night time, I will see this.
Sure, sure.
Yeah,
We'll discuss it next
yeah.
time. Okay, so next problem is for a FEM study, which of the plots of strain energy versus element size is correct? Which makes more sense.
Strain energy versus element size. Yeah, is greater. Yeah, as you have discussed this thing that when we refine our mesh, then always the strain energy stored in our FEM structure will in general gives the higher value or
Yes,
what it
yes,
is.
yes.
Yes,
It's based on that same concept.
yeah. I
So,
think
yeah, please go ahead.
B should one second. Element size. Okay, I think in that case A should be the answer because okay, point two, point
So
four.
let's analyze A first. Let's see.
Okay.
So A suggests that as our element size is decreasing,
Mm-hmm.
our energy is increasing. So that would suggest that as we are refining our mesh, as we refine mesh, we are getting closer to us to the exact solution. And so with a coarser mesh, we are far from our exact solution, and our energy is low. But where with a finer mesh, we are close to our exact solution. That is,
Okay.
so suppose we have exact solution somewhere here. This is our
Mm-hmm.
exact solution. So that means
Okay.
for our FEM solution here,
Mm-hmm.
the energy predicted was less than the exact solution. Is that right?
Okay. Okay.
But is that true? That's not true, right?
Yeah. Yeah. Yeah.
So FEM, the energy calculated by FEM should be uh, greater than the exact solution, right?
Mm.
And
Yes.
in the same way, C the plot C won't make sense because here the energy is fluctuating, going up and down. It should be monotonous.
Okay.
So our option B. So you see that suppose for this FEM solution, energy is this. Suppose we have our convergence here.
Yeah.
This convergence or we got exact solution, the energy equal to exact solution. That means our energy here is less.
Mm-hmm.
That means for our FEM solution, our energy was higher.
Okay. Yeah, but I didn't understand this horizontal axis also represents the actual level of energy for the exact solution.
Horizontal, you mean this h axis or
Yeah, because as you were saying, for
so?
example, as we are moving from the means, for example, I'm talking about this B option
Mhm.
here. When I give the refinement to our mesh,
Mhm.
so we are moving away from this h-axis, means this ordinate axis, it's showing the more value of the y coordinate. So what this means, this shows the difference between exact and the actual, or what it is.
Mm, you mean so this h axis represents the size of the element,
Okay.
right? So as we are moving left towards left,
Mm-hmm.
that means we are refining.
Yeah, yeah, got
So
it.
as we are refining, the size should decrease. So for
Yes.
each refinement, this can be understood as a plot for the energy for each refinement. So as we reduce the element size to say zero point 0.6, we
Mm-hmm.
got this energy. Now the element size is zero point 0.4. More refined mesh, our energy is this.
Okay.
Likewise, we go on increasing we go on increasing the refinement or reducing the element size. We see the energy keeps on decreasing,
Yeah.
and at some point it converges. The curve
Okay.
becomes flat.
Okay. Okay. So we have to decrease this as much as possible to for the solution to be converged.
Yes, yes, yes.
Okay. Okay. Yeah.
So energy would follow this path every time for any
Okay.
problem.
Okay. Got it.
You remember in lectures, there's a plot generated for some value like this.
Okay.
I think that's what some max temperature
Yeah.
versus I think number of degree of freedom.
Yes.
This plot is just opposite of this plot.
Mm-hmm. Okay.
So here the x-axis is the uh, number of degree of freedom. Okay,
Yeah,
that's
we
not
can
important.
we can, but we can directly relate this number of degree of freedom to the uh,
Yeah,
number of
it's the
unknowns. Yeah.
opposite of this h-axis here.
Yeah. Yeah. Yeah.
Okay, so yeah, that's what we saw there.
Okay.
Okay, so we just quickly do that here to find the energy norm and L2 norm, exact solution norm. So
This is very elementary problem.
yeah, yeah. So I'll just show you quickly how to do the energy norm part.
Yeah.
Okay, so energy norm is formula is almost similar except we have our domain is 0 to 1, right?
Yeah.
We have the derivative q dash of exact minus q dash of FEM. Rest all is same. So now we have the derivative of the solution.
Okay.
So
2x so x by 5 it is, and this one is
we have x by
by
5
10 square.
and we have 1 by 10.
Yeah. Dx.
So I'll just quickly do it on calculator.
Hmm.
Okay, 0.05c.
Hmm. Yes.
I'll just check the error in L2 norm also. I'll just don't write won't write it here. Right. Directly
Mm-hmm.
this x square by 10 minus x by 10 square. So I'll just change in the calculator. This x square by 10 minus x by 10 plus 1 square root. So this is 0, 1, okay, 2. Okay, so it's quite different than this.
Yeah.
Okay, yeah, so these are the errors. Next, I think still a few minutes we can see this problem maybe.
Weak form of the following coupled differential equation.
So we in this the lectures we haven't directly seen any coupled problems, right?
Yeah, yeah, yeah. No, no, no.
So this can be a useful exercise. I'll just quickly show you how to combine the two equations in
Okay.
this. So we take one equation at a time. So for this, okay, I will do this. I hope this the equation is not too complicated. Otherwise, I have
Mm-hmm.
one more problem. We can
Okay.
discuss this also, right? This
Yeah.
is a rather simpler problem.
Mm-hmm.
So we take first equation and we multiply it with the weight function phi.
Mm-hmm.
So I just quickly write we we'll do integration by parts and all that. I'll just quickly write the dp by dx du by dx. Uh, I'll skip the boundary term. We have pv minus pf dx. Okay.
Mm-hmm.
Then so this is weak form for first equation. Then for second equation, we have we take another weight function q.
Yes. d2e upon dx square minus g. It is 0.
So we'll have at the end we'll have x plus 1 dq by dx du by dx plus qg dx. So what we do is we take some for first equation. We can so for so we have two unknowns u and v, right? We can give some shape functions pi ui for this,
Yeah.
and for this we can give some other shape function psi I pi, and for uh, first weight function we can give this, and for second one we can use this for this. So it should be just to maintain the consistency. Yeah, this is better. So if we substitute these approximation functions in our weak forms, we'll have our equations as first equation would be uh, P is Pf, Pi comma x, Pj comma x, dx Uj plus we have uh, we have P is Pi
Mm-hmm.
V is psi j bj minus plus f equals to pf. So this is p is pi I to f. Okay, then for second equation we'll have psi I comma x psi j comma x figure bj. Then we have minus of psi I g dx. So
Yes.
we'll combine this in terms of matrix, one big matrix. Here the this can be first part of this row vector is uj, another
UJ.
one is
Yes.
vj,
Okay.
and here first part would be from the f, other would be from g,
Yeah.
and here we'll have, say this is k1 2. So just put that k, sorry, 1 1, k1
Yeah.
1, k1 2, say k2. So this is, so coefficient of u would come first, and then coefficient of b,
Mm-hmm.
and then again in second equation there is no coefficient of uj,
UJ. Yes.
so
It is
we have
zero. Yeah.
f k2.
And here at K2.
So
Okay.
that's how we'll combine into the into one stiffness matrix. For each element we'll do that.
Okay.
So that's how we deal with coupled problems. In elasticity equation, we don't break it down into two equations and solve it.
Mm-hmm.
There are ways to deal with it directly, but in usual coupled problems, we have to do it this way.
So coupled means we are using means there are two type of analysis or two type of deck we are using. For example, first I want to distribute the temperature within the FEM structure based upon the boundary condition, and then again I will use this into the static structural analysis or transient structural analysis to get the stress results.
Okay, there are different approaches for coupled problem actually. I
Okay.
think one is called staggered approach, and another one is called. So in one of these approaches, we evaluate one variable first, and
Mm-hmm.
use the value of that to evaluate the other variable.
Okay.
Uh, that that is staggered, I think.
Okay.
And there's another where we solve the two variables simultaneously.
Okay.
So staggered approach could work for this problem, because in second equation you see we don't have u, so it will
Okay.
directly give us v, and this v from here we can use up there to evaluate this. But in two-way coupled problem where we have u and v coming in both equations,
Mm-hmm.
it's sometimes better to use the simultaneous approach where we solve
Okay.
for both simultaneously.
Okay. Okay. Got it.
Okay,
Okay.
so we'll conclude it now. Uh, if there's any doubt, if you want to discuss, we can address it now.
No, there is no any doubt.
Okay. Otherwise, the course is going fine for you.
Yeah. 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 Course is going fine.
Okay, good.
Yeah, but still, I'm doing some struggle with MATLAB actually.
Okay, MATLAB. MATLAB is it's up to you. Whatever you find comfortable for that for programming. They
Okay.
have just chosen MATLAB for this course. But if
Mm-hmm.
you want, you can. If you're comfortable with Python, you can go with Python or C++,
Yeah.
whatever is convenient.
Okay. Got
But
it.
for my fund of a programming is I'm not very well acquainted with all these languages. So
Okay.
whenever I have to deal with any particular language, I just keep on searching the syntax and queries for that
Okay.
simultaneously. I don't
Okay.
remember anything all the time. It's hard to do
Okay.
that. You have to work with multiple languages. So I simultaneously troubleshoot whatever has to be done.
Okay. Okay. Got it. Okay.
Okay.
Fine.
Yeah. So thank you so much for joining the session.
Okay.
I'll see you again next time on Tuesday.
Okay.
Thank you.
Okay. Bye.